Hello and welcome to Tensile Ground Coffee, a few minutes on ground engineering to enjoy while having your coffee. Well, because of the lockdown, we're back in the kitchen again. What I'd like to do is to demonstrate to you the remarkable performance of aggregates when they have the benefit of some confinement, some lateral confinement from geogrid wrapped around them. So I'm going to do that using objects from the kitchen. So my aggregate, like before, is going to be these chickpeas, which are like gravel. And I have some netting from the garden here, this plastic netting, made by a similar process to our geogrid, but scaled down, of course. Now, if we wrap this into a cylinder, like so, and then fix it with a stapler into a cylindrical shape, then fill that cylinder with the chickpeas. There we go. And let's see what weight that can support. So I've got quite a heavy bottle here of fabric conditioner. Let's put that on top of that cylinder of aggregate contained in the grid. Look at that, it can support it. Now the reason that the chickpeas can support that quite substantial weight is because they are being confined by the geogrid. So as we compress the chickpeas, they want to expand laterally, but that is resisted by the tension in the geogrid. That is a hoop stress, it's called. And in effect, that is giving the soil or the chickpeas tensile strength. Gives it a cohesion when acting as a composite. And also the higher confining stress means that it would actually be stiffer than if the geogrid wasn't there. But if the geogrid wasn't there, what's happening to the chickpeas? Of course, it just collapses. It can't support the fabric conditioner without the benefit of the grid. And in a similar way, the geogrid on its own can't support the weight of the fabric conditioner. It's a classic composite. You need to have the two materials together in order for them to provide a useful function. Now that was a cylinder, but the geogrid doesn't need to be in a cylinder. It can be in other shapes as well. So I've got another piece of the same mesh, the same geogrid. So I can staple that into a sort of triangular prism shape, like so. So let's put that on the worktop and let's fill this one with chickpeas, and let's see if this will support the weight of the fabric conditioner as well. Just fill it up. There we go. That also supports the weight of the bottle of fabric conditioner, and it's working in the same way. The advantage of this shape is that it tessellates. Now, you remember that word from your maths at school? It means that we can fit together lots of these, and they will fit together without overlapping and without leaving gaps, which you cannot do with the cylinder. So, Tensile has this remarkable application. Its scientific name is a cellular mattress, something like that, cellular foundation mattress or basal mattress. We call it stratum, which is a lot easier to remember, of course. And that is it's an arrangement of these shapes of geogrid. So when you construct it, you start off with a geogrid at the base. So we use our triax geogrid at the base, and that provides a platform on very soft soils on which people can walk. And then we get the uniaxial geogrid, and we lay it vertically in parallel lines, and in between them we lay a zigzag pattern of geogrid in between. Now, because we've been at home for quite a while due to the lockdown, had a lot of spare time, so I actually made my very own model stratum. So that's what it looks like. So on the base, that's the geogrid that is laid down on the base. These are the long pieces of grid that go across, and we have these zigzag pieces here, and you see that we have lots of these cells of the same shape as that. So if we filled that with an aggregate, imagine what the performance of that would be. So how can we test that out? Well, what I've done is this dish here, I have filled it with this natural yogurt. So it's about half full. And I've made it all flat on the surface here. So this has the consistency of a very soft clay, as you see there. But it tastes a lot better. So this is quite a good material available in the kitchen that we can use in an experiment to see how this stratum would perform on a soft clay, because that's where it's used in practice, where we have very soft soil deposits, soft clay, soft peat, that sort of thing. But so I don't get chickpeas mixed up with yogurt, and I don't think chickpeas and yogurt go very well, certainly not raw chickpeas, I'm just going to put cling film over the top of the yogurt. So it shouldn't add a lot of strength, but it's just going to stop the chickpeas and the yogurt all mixing together, which is going to create a real mess. So let's put that in there, down like that. Let's cut that bit off. Okay. I think that's all ready. So we've still got a very soft surface there, but we've just got the cling film to separate it from the chickpeas. So I can put my stratum in there on the top like that. So I've built my stratum. I'm now going to fill it with my aggregate, or in this case, the chickpeas. So of course this would be done in real life by an excavator, filling these up in a progressive fashion. So that's pretty much full. Let's just distribute them a bit so it's all flat. There's a little gap there. So I think we're just about there. So let's see how that performs on this soft yogurt. Let's go for the heavy bottle of fabric conditioner again. Okay, that seems to work pretty well. Not a lot of settlement there. Let's try a bit more. How about adding a bag of sugar as well? A little bit of settlement, bit of compaction of the chickpeas, not much settlement of the yogurt, I don't think. So you're getting in close there, Brian. You see that all looks still quite flat, doesn't it? Looks pretty stiff. It's distributing that load to the yogurt very effectively. Now, of course, we want to compare that with what the performance would be without the stratum. So imagine if we just had chickpeas and no stratum. So there, look at that, that's quite flat. Let's get a straight edge there. There's a slight depression, but not much. That's pretty flat along there. So imagine that we just had a layer of granular material without the stratum. Let's spread that out. We might need to top it up a bit more just to make sure we got the same thickness of material. Okay, I think that's ready. Let's try the fabric conditioner then. On it goes. Oh, I can see a lot more movement Let's put the bag of sugar on as well. Ooh, that doesn't look as stable as it did before, does it? I can see we're getting more settlement of the bottle, and I saw quite a lot of heave coming up on each side, so I don't think that is working nearly as well as the stratum system. So what I'll do is I'll take out the chickpeas and we'll see if there's been any settlement in the yogurt below. Oh, look at that, quite a big divot left in the gravel there. Let's get this bowl. Try not to make too much mess. There, quite a big depression left in the yogurt. There, it actually went right down to the base, look. It pushed all the yogurt out of the way. But with the stratum, we didn't see any of that movement at all. So, isn't that good? All from the kitchen, using objects in the kitchen and in the garden in the case of the GeoGrid. There's a demonstration of the remarkable performance of the tensile stratum system at distributing loads, perhaps from a crane on a platform or an embankment built on very soft materials, such as this yogurt. Okay, that's all for this episode of Tensile Ground Coffee. Thanks for watching and see you next time.